In 2024, on Christmas Eve, the majority of the world was focused on earthly celebrations. A spacecraft no bigger than a small car was speeding through space at a rate no man-made object had reached before, for 130,000 miles per hour. This was NASA's Parker Solar Probe, and it wasn't just breaking records. It was venturing into a realm we had only imagined. At just 3.8 to 8 million miles from the Sun's surface, Parker soared through the fabric of our star, touching the actual corona. For the first time in human history, we were not just watching the Sun from a safe distance. We were a part of its atmosphere. It wasn't just what it captured there that was stunning, but also unsettling. Applying AI to decode its final and most daring images, scientists discovered phenomena that defy our solar physics models. In the depths, massive eruptions collide, spiraling magnetic structures as violent as cosmic ballet dancers, and bursts of switchbacks that twist the solar wind into forms that look almost impossible. These discoveries could change everything we thought we knew about how the Sun works and how it can affect life here on Earth. Parker's December 2024 flyby was a milestone, not only because of its proximity, but because of the clarity of its data. The spacecraft's Wide Field Imager for Solar Probe, known as WISPR, recorded streams of solar plasma flowing in real time away from the Sun. But this wasn't just another view of solar energy. These were pictures taken at the exact point where the solar wind is born. Each glint of light in those frames was a particle moving quickly at hundreds of miles per second, carrying the Sun's magnetic field throughout the solar system. In the midst of this torrent, Parker caught something remarkable: 3 separate coronal mass ejections, CMS, within a matter of hours, erupting from the Sun. In the past, we've seen CMS from a distance, days after their eruption. But Parker's vantage point allowed us to watch their birth and, more importantly, their interaction. What the AI discovered was unprecedented. These 3 CMS did not simply travel outward. They collided, merged, and formed what scientists call a cannibal CME, a solar wave with immense power, material, and magnetic energy. The scale of the combined eruption was staggering, and its potential implications for Earth are extremely worrying. In the last image from Parker's flyby, another structure emerged, one the AI recognized as the heliospheric current sheet. This vast, spiraling boundary is where the Sun's magnetic field changes from north to south. Arena's endlessly spinning skirt, spanning billions of miles across the solar system. This sheet is not just a passive feature, it actively shapes how solar wind travels and how CMS strike Earth. Changes in the heliospheric current sheet, from Earth's point of view, can mean the difference between a harmless aurora and a global technological crisis. When CMS align with this magnetic boundary, they can direct their energy straight into our planet's magnetosphere, bypassing much of our natural shielding. AI analysis of Parker's latest data suggests that the current sheet is significantly more dynamic and turbulent near its origin than previously thought, constantly reshaping itself as a result of magnetic activity deep inside the Sun. Back in 2018, Parker had discovered strange zigzags in the solar wind, dubbed switchbacks, rapid reversals in the Sun's magnetic field direction. At the time, they were thought to be random turbulence, but during this latest flyby, the AI uncovered something more disturbing. The switchbacks were aggregating and forming patterns and waves that recurred over time. Some of these patterns lined up with the timing of the CMS Parker had observed, suggesting a link between the two. These switchbacks may be the long-awaited key to one of solar physics' greatest puzzles: why the Sun's corona is several hundred times hotter than its surface. If these magnetic whiplashes are conduits for energy movement, they may be pumping heat into the corona at astonishing rates. However, there's also a darker implication. If switchbacks can amplify the speed and energy of CMS, they may be a covert trigger for some of the most dangerous solar storms in history. Reaching this point was no easy feat. Parker's approach was made possible by a series of gravity assists from Venus, each one slingshotting the probe closer to the Sun and faster than any spacecraft before it. During this pass, the carbon composite heat shield endured temperatures over to 600 degrees Fahrenheit 400 degrees Celsius as levels of radiation bombarded its instruments at intensities that would quickly destroy most satellites. Despite the harsh conditions, Parker returned more data than scientists expected, so much so that AI assistance was required to process it all before the probe's next encounter. This close collaboration between human researchers and artificial intelligence is what allowed the faintest patterns like the hidden turbulence in the current sheet, or the synchronized switchbacks to emerge from the abyss of noise. These findings not only redefine our understanding of the Sun, but also hint that the most dramatic revelations may still lie ahead in Parker's final orbits. As the AI combed through Parker's imagery, it detected an anomaly unlike anything in the existing solar catalog, a large, elongated area in the solar wind where particle density dropped close to nothing. Scientists have long understood that the solar wind is not uniform, but this void was something else entirely, a sharp, clean boundary stretching millions of miles with almost no charged particles traversing it. Even more troubling was the fact that this area surfaced immediately downstream of one of the cannibal CMS Parker had observed. According to the AI models, it's possible that the CME acted like a cosmic broom, sweeping particles away and leaving a huge corridor that looks like a vacuum beneath it. Although visually stunning, the phenomenon sparked deep-seated concerns. If such a low-density corridor were to intersect Earth's magnetosphere, it could temporarily compromise the planet's ability to shield against radiation, increasing our susceptibility to cosmic rays and energetic solar particles. This was no longer confined to space science, it was a planetoid defense issue. Additionally, Parker's instruments detected subtle changes in how the Sun's magnetic field moves during the flyby oscillations that humans cannot detect. Analysts had previously dismissed them as noise in the data. However, the AI found a magnetic heartbeat, a pattern pulsing roughly every 140 minutes. What set this apart was the rhythm that appeared in multiple data streams simultaneously: magnetic readings, particle velocity shifts, and even extreme ultraviolet light fluctuations. The conclusion was extraordinary. It's possible that a coherent global process, occurring deep within the Sun, regularly modifies its outer layers. Some researchers hypothesized that the mysterious pulses could be linked to solar cycles that drive sunspots, CMS, and solar storms. If this is the case, the AI might have uncovered a predictive tool, one that could alert us to potentially lethal solar events before they take place. However, as with all brand new findings in Parker's data, this knowledge came with a question: if such a signal exists, why are we only spotting it now so close to the Sun? One of the most shocking revelations from Parker's final imaging session was the discovery of a huge filament of plasma rising from the Sun's surface, a structure so large it spanned nearly 2 million kilometers in length. Typically, such filaments eventually collapse back onto the Sun, releasing energy in isolated eruptions. But the AI analysis predicted that this filament was unstable in a way we had never previously recorded. Its magnetic anchoring points were weakening, and when it finally erupted, it could launch a magnitude scale CME stronger than those in the December triple outburst. If this prediction is correct, and if the eruption corresponds to Earth's orbit, the resulting geomagnetic storm may be similar to, or even surpass, the illustrious Carrington event of 1859, a solar storm so powerful it set fire to telegraph wires and produced aurora visible in the Caribbean. In today's hyper-connected world, such an event could disable satellites, shut down global communications, and disrupt electrical grids for weeks or even months. Perhaps the most puzzling find of all came not from the images, but from the radio data Parker sent before completing its flyby. Buried in the telemetry was a narrowband signal that repeated, matching no known instrument signature. The AI flagged it as a non-random, structured modification based on Parker's immediate environment. Put another way, the signal seemed to be coming not from the Sun but from the space around the probe itself. It wasn't strong enough to be a definitive sign of anything artificial. However, its timing coincided precisely with Parker's traversal of the most intense region of the corona, raising eyebrows. Some scientists cautiously suggested that it might be pure plasma resonance amplified by the sun's magnetic field. Others, however, quietly wondered if Parker had stumbled into a region where plasma interactions behaved in ways our physics can't yet explain. Either way, the signal's origin remains a mystery inside the probe's last batches of data. The Parker Solar Probe was built to answer our oldest questions about the sun, where the solar wind begins, how the corona reaches unimaginable temperatures, and what forces drive the storms that can reach across millions of miles to touch Earth. It was never intended to return. The journey was a one-way trip into the most hostile atmosphere any spacecraft has ever encountered. But what it provided before fading into the sun's embrace was far more than anyone had anticipated. The AI-assisted decoding of Parker's final data didn't just enhance our view, it shattered preconceptions. Cannibal CMS merging into colossal storms, the magnetic heartbeat pulsing deep within the sun, the vast plasma filament poised like a serpent in a spiral, and the mysterious signal in the corona, each finding on its own, is extraordinary. Together, they tell us the sun is not the steady, dependable star we once imagined. It's a living, restless engine capable of doing things we've never seen before and perhaps are never fully prepared for. The potential of some of these discoveries is key to predicting and protecting ourselves from the sun's future catastrophes. Others suggest processes we are still far from understanding. And then there's the signal, the one anomaly that sits outside every known category, a whisper from the most violent location in our solar system in a dying probe's final account. Whether it was a natural plasma resonance or something stranger, its presence forces us to admit that we don't yet know everything possible inside the sun's domain. Parker's journey has ended, but the data it left behind may take years to fully comprehend. The sun has always been in our sky throughout the entire history of humanity, but the closer we get, the more obvious its dynamic, unpredictable, and occasionally dangerous nature becomes. We now know that our survival as a technological civilization may one day depend on our comprehension of its moods and how quickly we can act when it changes. That may be the most sobering truth of all. Parker didn't simply bring us closer to the sun. It brought us one step closer to the day we will have to face its full power.